Okay, good afternoon everybody, once again. What I'd like to do is revise very briefly 5 minutes per tutorial for tutorial 1 and 2, which are already up on YouTube. To find them, as you know, you just put my name into YouTube and they'll come up straight away. And hopefully this one also in about a week's time. Today we're going to cover photo detection. In tutorial 1 we covered the lasers, and in number 2 number 1 the laser, the fiber, and number 2 the lasers. The type of fiber we use for telecommunications, it's an example there. It's got multiple cores in it, and that telecoms fiber is as different from these, which are simply illumination carrying fibers. They're as different from one another. I could say as different as chalk is from cheese, but today I'm going to say they're different from one another as arithmetic is from mathematics. And the reason I say that is in tutorial 1 and in the first part of this book, available on Amazon and Lulu.com, the first chapter and topics in that take a stick of glass like that and use this basic arithmetic to analyze the dispersion. The rays that go straight down the axis and the rays at an angle that take longer. That spreads out the pulses. Dispersion is the enemy of bandwidth. In actual fact, turn one upside down and you've got the other. So, arithmetic is what's sufficient to show the bandwidth of those kind of fibers was about, those illumination ones, maybe a 10 or 20 megahertz times kilometer. It's useless for modern day communications. This is hundreds of gigahertz times kilometer. Massive difference. And the way we did it is we used mathematics, we used the wave equation, not arithmetic. We solved the wave equation in a cylindrical guide and we came up with the phase expression, call it S of R. E to the power of I, S of R, was the oscillating wave, where S of R was the phase. For E to the I, S of R to oscillate, S of R had to be real. And we looked at the conditions for that. And that showed us what the modes looked like. And the mode of the fiber, it turned out, looked somewhat like the modes of this, because there's a lot of similarities. This is a cylindrical guide. Now I'll tap it here in the center. Now out here. Notice the difference in pitch? And the reason is, when I tap it there, the center is oscillating and the rim is silent. When I tap it out here, I excite an oscillation in a ring here. It's silent in a ring inside that, and it's vibrating in antiphase in the center. So the center, when it's moving out, this ring is moving back, and it's silent in between. And there are two of the modes, the lowest modes of vibration of that acoustic setup. Now, our cylindrical guide is similar to that. Our wave is traveling down, and we expect the standing waves to have a pattern which is which is some kind of an oscillation, a peak, a trough, and a peak for each mode. The lowest mode has just got one peak in the center and fades away to the edge. And that gave us a clue how to look at the mathematics of light in the fiber. There were two major challenges to go from that stick of glass to a modern telecoms fiber. The first one was, rather than having a stick of glass, you have a refractive index profile. That means you've got a cladding. The cladding made a huge difference, because when the light reflects totally internally, much lower order modes reflect, and there's less modal dispersion. The second thing was, how did you get that refractive index profile perfected? And we studied that and found, using the method of Bell laboratories in the States, that you use a refractive index profile with a power factor. And when the power factor was 2, we found there was a massive dip of 10,000, factor 10,000 in the dispersion. So a parabolic index profile was what we needed. Then we said, how do you get rid of all the modes except one, except that lowest order one as on the drum there? Then you'd have no modal dispersion because you only have one mode. And that's what we've got here, single mode fibre. And the way we did that was, maths again, we went away to the library and spent a month studying cylinder functions. Because it occurred to us, these have to be cylindrically symmetrical, these patterns. We came back after the month and we said, hey, it looks to me like the function suitable for the core of the fibre is a Bessel function because it's got oscillations in it, just like our drum. And some of the light, because of the cladding is there, some of it translates out into the cladding. And that evanescent field travels along as well. But it decays almost exponentially, that type of a pattern. Cylinder function that has that property was the Hankel function. So we wrote the Bessel function expression, and we put it equal to the Hankel function expression, where they had to be equal. There had to be a smooth pattern transition from the core to the cladding. They had to be equal at the interface. So when the radius r was equal to a, where a is the diameter of the core, the two were equal. And then secondly, the derivatives of those had to be equal. So there was a smooth transition. That gave us two equations. There were two variables in the expressions we could solve for them. And from that we found the condition needed to cut off all the modes except the lowest order mode. It was expressly an equation that wrote V sub C equals 2.303, because 2.303 corresponded to the lowest order Bessel function. Okay, so that's a quick summary of the difference between arithmetic and maths. Then we did lasers in tutorial 2. And we worked out how to develop the double heterostructure laser, which had three kinds of confinement. It confined the carriers, confined the light, and it confined the current. And that gave a massive leap forward in optical telecommunications. That happened about 25, 30 years ago. As the years went by, 10, 15 years ago, another massive leap, and we covered that near the end of our lasers, was the quantum well device. Strangely, the analysis of the quantum well device also required looking at these kind of standing waves. Because this time it was not light we were worried about, it was electron waves. By confining the active region in a quantum well laser to 200 angstroms or less, only the lowest order 1 or 2 electron standing waves were sustained inside in the active region. The advantage of that quantum well device, and we had to use de Broglie's equation for electron waves to do that, instead of the wave equation as in the fibre, but it is a similar type of approach. We confine the active region. In the fibre we confined the core, and to get a single mode. Right? By doing that, it means it is very easy to cause a population inversion in the laser. It only took a small amount of pumped current to get more carriers upstairs in the conduction band and were downstairs in the valence band. And that meant you got more stimulated emission than spontaneous emission. That is the first condition for laser action. So that was the quantum well laser. And we then learned that you could tune the lasers. And I picture here what we might be doing. You would have a quaternary transmitter. There's the laser. And if you could tune it, well then you could work within the C-band, conventional band of optical fibre. The losses diminish in the visible, drop as you go into the infrared, and then there's a peak due to residual water, and then you hop into the C-band. That's where all our modern telecoms operates. But the C-band is broad enough to fit 100 or more channels if you could tune the wavelengths to the fine channels. And we learned how to do that. And that's called wavelength division multiplexing. It means immediately you can multiply the bandwidth of the fibre 100 times. We even saw you could tune the laser electronically, and my group put out a paper for the millennium, 2001, showing we could tune to 2,000 channels with a tunable chip laser like the one in the picture you saw. And we could still satisfy all the requirements for signal to noise ratio and all the rest, all the other technical requirements. Alright, well that's the review of what we've done so far, and we're going to now concentrate on this end of the system, which is the receiver, which then feeds into a low noise amplifier, LNA. So that's a microwave device which amplifies the photo-generated photocurrent. Right, let's get on then so with these detectors. We'll start off with a simple photodiode. We saw that silicon does not work for lasers because it was indirect band gap. And we studied that process. And we found that we had to search for new semiconductors. We found them in ternary and quaternary alloys made of indium, gallium, arsenic and phosphorus. And then we learned how to grow those alloys into layers. But you could use silicon for a detection, however, not in the C band, only in the visible and the near infrared. So we might start off here with a silicon diode, but we'll migrate to gallium arsenide and then indium, gallium arsenide and other quaternaries. Simple diode, we reverse bias it, the opposite to a laser, which is forward biased. We will have an N plus layer on the bottom. That's to give good metal contact, good contact with the metal, because the N plus heavily doped. It's good conductive properties. Then we'll have an N layer, lightly doped. Then we'll have a P plus layer, heavily doped P plus, and we'll have a window above in this silicate or oxide layer to let the light in. That's our basic photodiode, primitive one. What happens now? The photon enters and it's absorbed in the depletion layer. So here's a picture of the P plus N. As you know from your electronics, which we call on several times now, your P plus layer being heavily doped, the depletion layer only penetrates a small amount. On the other side, it penetrates a good bit on the N side, which is lightly doped. So the E field rises and falls away more slowly. And all the light has to be absorbed in that depletion layer. Now you'll have the choice of increase the voltage. Depletion layer will spread out like that, and you have a bigger volume to absorb the light, create carriers. The alternative, and the trouble with that is you have to keep increasing the voltage. The alternative is put an intrinsic layer in between. And that increases the volume. Here's the depletion layer again. E field rises, falls slowly because intrinsic has a higher resistivity. It's not as good a conductor. And then falls away again. So we have all this big volume for absorption of light. In terms of the energy levels, there's the light arriving into the depletion layer, and an electron is excited up into the conduction band, and the electrons are swept out by the E field and the holes in the other way to give the external current. Now, if you don't have an external voltage and use that, you'll get a voltage at the terminals. That's called photovoltaic mode. However, for telecoms, we use the other arrangement, which is the photoconductive mode. Now let's look at this diode and see how it behaves electrically. Photons create carriers, as we've just seen in the energy level diagram. We call that I lambda, current at wavelength lambda. That's represented electrically by this photo generator, current generator. And that's a generator is part of the photodiode. So there's the photodiode. Some of the current will leak through the diode, ID. You know the characteristic of a photodiode is kind of exponential in the plus side, and it then flattens out on the negative side. So we have that leakage current. That's passing through there. Every diode has got a shunt resistance and a series resistance. So we include them. And finally, because the diode has got a layer of plus charge and a layer of negative charge, with a gap between, it's acting as a capacitor. So we have a diode capacitance. We have to take all of those features into account from an electrical model. Okay, you can very quickly write all of these and you have a glance at them. The current splits up as Kirchhoff's law into these three, and then the external current. But that current originally is coming from, this is an important part to explain to you. The photo generation occurs because light arrives. I'm calling that the irradiance. The irradiance is the watts of light falling on each square meter. Right? Of course, we'll only have maybe 100 microns by 100 microns, so it'll be a fraction of a square meter, but nonetheless, that's the units of it. So the watts per square meter multiplied by the area of the window, that's the window of the photodiode, divide by the energy, so that's joules per second now, and divide by the joules in one photon, and now we've got photons per second. Photons per second multiplied by electronic charge is current per second, charge per second, and then there's an efficiency factor there. Now the rest of this is just Ohm's law and Kirchhoff's law, except for that one, that's the diode equation, exponentially on the plus side and minus I naught leakage current on the other side. Okay, we'll talk about silicon and then leave it behind. Typically with a silicon diode, 10 volts, and the leakage current is pretty small. I've written it down there for silicon, about 10 nanoamps, I naught. Typically, you'll have microwatts arriving at a receiver of light, producing microamps of current. So I lambda is of the order of microamps, and then the shunt, you put this voltage over this resistance and you'll get that current. Typically 100 megs for silicon, 10 volts reverse bias, it's 100 nanoamps. Now you compare those numbers, silicon, and you can see you have 10, 100, and 1,000 nanoamps. So this thing here is 10 to 100 times bigger than the others. So you can write external current is equal to this. In photoconductive mode, you can ignore that. If you want to be very careful, though, you have to include it, because that is the sum of those, the diode current and the shunt current, are still trickling away there, even if you switch off the laser. So we call that's the dark current, and it's noise. It's the dark current is shock noise. Okay, the important thing about that analysis that I want to show at the end here is when you substitute one into the other, the external current depends on I optical and lambda. Depends on the irradiance, how many watts per square meter are you receiving. That means we have a linear response, crucial. In the book, we do the photovoltaic mode as well, and it's a logarithmic response, very highly nonlinear. Second thing is, it's proportional to lambda. So I'm going to take a look at this now and talk about the response. Okay? The response, if it makes sense, was how many amps do I get for every watt of light. So I optical times A is the watts. I bring that across, and the response is amps per watt. And we can see that expression has got a lambda in it. I brought across the I optical A, and I divided it into the amps I get out. So that's light in for current out. So that's our definition. Triple equal sign there for definition of responsivity. Okay? What's left on the other right hand side when you did that on the last equation, there's a lambda there. Everything else in the bracket is a fundamental constant, fixed constant. Fundamental, and the efficiency of the device you constructed. All right? This tells us there's a graph of responsivity against lambda should be a straight line. So there's our ideal straight line. Now, that raises a question. Why on earth would the diode be getting more and more and more responsive as you go further and further and further into the infrared? And it's going up linearly with it. clue if you think of what happens in reality. In reality, yes, it does rise, and with silicon it suddenly cuts off at 1.1 microns. And that's because the band gap in silicon at that stage is too big to absorb any more photons. The photons are too small. So that explains this linear rise as well. The further you go out in lambda, the smaller the photons get. Therefore you're going to get more photons per watt, and therefore more electrons per watt. So the responsivity goes up. Alright? So, you can then migrate to germanium, because cut off at 1.1 is no good for us. We need C-band. But germanium is it's too much for the other side. It's cut off. Shape is exactly the same, but this wavelength here is 1.8 microns. We're working at 1.55. That means the gap in germanium is so narrow, you get an awful lot of noise generated. Carriers hopping up and down and all over the place, even in the dark. So that's no good. So then we've got to go back to our old ternaries from our lasers and work out what alloy cuts off just beyond C-band. Turns out gallium indium arsenide, in the ratio of you substitute arsenic atoms for indium atoms, you substitute 47% of them, and you'll get a cut off neatly at 1.6, just beyond the edge of the C-band. That's good, because we're going to minimize the noise in that way. So that would be a ternary photodetector diode. Now, another approach is to improve, instead of going into a low noise amplifier, can we amplify internally first and use, of course, the avalanche effect? So we make the voltage so big, maybe 50, 60, 80 volts, minus 80 volts. And when you generate carriers, they bang into others and ionize them, and you get an avalanche gain. Trouble is, that's a statistical process. Two things are happening. The coefficients of ionization for electrons and holes, I call them alpha and beta in the text, they are highly dependent on the electric field and on the temperature. So there's going to be a spread. If the electric field is wobbling up and down, there's going to be a spread of multiplication factors. And if the temperature inevitably is going to drift up and down, no matter how good your thermal control, same thing. So we have a statistical average of multiplication factor, typically 10 to 100, depending on, are you using minus 50 volts or minus 80 volts? We need an automatic gain control to make sure the E field inside the diode is not wandering too much. That's the price you pay, along with the high voltage. Add a photo regenerator in a manhole in your network, you're going to have 80 volts supplied instead of simple easy volt like 5 or 10 volts. And you're going to have good thermal control there. So you're going to need a lot of conductors in your cable as well. You're going to have to supply your high voltage, and you're going to have to supply current to your thermoelectric coolers in order to stop the spread of M. So there's an operational cost involved in using the APD. A third possibility is use the pin, and you don't have all that statistical scatter problem with M, and integrate an FET on the same chip with it. Rather than coming from a pin out to a low noise amplifier into a box, have the whole lot on one single chip, and you get rid of an awful lot of the parasitics and the noise associated with it. So the pin FET is a very common solution. A picture of that, of one of those things in the book. While I talk about pictures, I should say once again, all the diagrams in that book are simple line diagrams with the purpose that you redraw them. When you come to every diagram, redraw it, no matter how quickly you scribble it, you will then memorize an awful lot, and you will absorb what the heck is it all about. Where are the cutoff points? Where are the peaks? Where are the important numbers? So redraw every plot. Well, we talked about the photo generation process there. and we talked about statistical noise from the avalanche gain. So we can now put one of those over the other and get the signal to noise ratio. As I said, when we carried out that experiment for 2,000 wavelengths, we had to make sure the SNR at every single channel satisfies the International Union's requirements, or the ITU standard. So what is the signal to noise ratio? Let's take a laser transmitter and we'll modulate it sine waves, sine of omega t. Right? And we'll have a modulation of index of maybe 80% or something between the peak and the bottom. So it might go from 100% to 20%. So that's a modulation index there, 80%. Now you might say, well, look at the bits in this network are actually rectangular. But of course, remember, a rectangle or any other shape can be made up of just a Fourier sum of sine waves. So if you can analyze it with this sine wave, the same applies to all the other Fourier components in whatever shape of signal you're using. Okay, so that's what we transmit. Then down at the detector, the average photocurrent is I0. We had an expression for that a minute ago. It involves the received I0A power and the efficiency Q. So we know what I0. Then it's multiplied up by M, and it's still got a modulation. That's the signal. Then there's the noise. We usually use the mean squared when we're dealing with noise. The mean squared total noise made up of the circuit noise and the shot noise. The circuit noise is down here. It's from basic electronics for your low noise amplifier. Whereas the circuit thermal noise contains temperature T, bandwidth, and a noise factor for the low noise amplifier, and also the input load resistance of the amplifier. So that's the circuit noise there. And the other component is from the light scattered in the photogeneration process. Again, when you have a current I, the shot noise is twice the I times B from electronic communication theory, twice the IB. But in our case, we multiply up by M, because we have an avalanche gain M, and then the noise on the avalanche current is also multiplied up by M. So there's an M squared there. And furthermore, there's this statistical factor for the scatter in M. We call it the excess noise factor. Okay, put one over the other and you've got the signal to noise ratio. Just note when you do that, you've got to mean squared that trig expression there. So you'll get I0 squared, M squared, and this averages to a half little m squared. It's commonly occurs that type of, we have to average it in communication theory. So the half m squared is from the bracket. I0 is squared up to get the mean squared, and then this is the remainder. That's our signal to noise ratio. We then use that as follows. This gives us an idea as to when and when not to use and how to use an avalanche photodiode. But to simplify it, I'm going to take the pin expressions here, and I can say, imagine that the photocurrent is very small. You have a very weak signal arriving, photo signal. Then you're going to get a very small current. If the current is very small, it means you can only discern one or two, maybe two levels. That's telling you that's only satisfactory in a digital system. On the other hand, if I0 is large, it means you can discern lots of levels within its range, and that's suitable for an analog system. So we take those two extremes. One of them contains the circuit noise term, that's the circuit noise limit, suitable for digital. The alternative is the shot noise is dominant, because there's a lot of light, so there's a lot of shot noise. Okay? So the circuit noise can be ignored, and that is the shot noise limit, and that's suitable for analog systems. Final thing to say about that is that particular limit there, if the circuit noise is totally ignored, you're saying that's a perfect receiver. There's no circuit noise. That means all the problem is in the quantum nature of the light. So that is the fundamental quantum limit. that expression there. Quantum limit as well for light. That's the limit you would use in extreme cases. Say somebody's in a spacecraft orbiting Mars and they're pointing the laser at Earth, sending information on the laser beam. You're going to have a very weak signal. You're going to have to make sure you're above the quantum limit, or you might as well forget about the link. Alright. The final thing is that signal to noise ratio there. Well, you can see there's an optimum in it. As you increase the voltage, M goes up. It starts at 1 for a pin, mean M, and then it rises and rises as you head for it towards an APD, a lot of avalanche. And as it does, this expression here, this expression, initially this expression is dominant, and as you go higher and higher, you get a lot more avalanche, and this M squared cancels out this M squared, that can be ignored, and the signal to noise ratio falls off according to F of M. F of M is underneath that. So, as you change the voltage, you get to a maximum SNR. That happens when the two terms underneath the line are equal. And then when you go beyond that voltage, have a bigger multiplication, this SNR goes down again. So in other words, we conclude that the SNR is optimum when the circuit noise and the shot noise are equal. After that, it falls off. Quicker way if you want to do it is just differentiate. Imagine changing the voltage, in other words, the multiplication factor. Differentiate that with respect to M, you know, the UV minus UV, U or all the rest of the expression for a quotient, and you'll get the same result. Right, I'm going to finish off. I said I'd try and finish with less than the hour. I'm going to add one little thing because I think you'd be interested in this. It's not in the chapter there, but it's a very simple thing, and you'll see why I want to do it. In binary photo detection, no matter what the bit rate, right, whether it's a local area network at 100 megabits per second, like campus network here, or whether it's an intercity network at 10 gigabits per second, 100 times higher, you still need 21 photons in every bit, no matter how many bits you squeeze into the second. Right? And I'm going to show you why very quickly. Here's our transmission of bits, 1, 0, 0, 1, 1, and so on, random bit stream, from transmitter to receiver. Okay? The period of the bit interval is T, and 1 over T is the bandwidth, bit rate per second, should I say. In the photo generation process, you get some errors. Okay? The error rate that's allowed in telecoms today is 1 in 10 to the 9. The bit error rate must be better than 10 to the minus 9, 1 in a billion. And you say well, that's a bit much, isn't it? But it's not, because if you're transmitting a gigabit per second and you're at 10 to the minus 9 error rate, then you're getting 1 error every second. Well, you wouldn't want to have a lot worse than that in the telecom thing. So you need, and indeed, if you were in finance, a link between Citigroup maybe and their headquarters, they might want 10 to the minus 12. So in any case, that's the kind of error that you want. What is it made up of? The probability of an error is the probability that the receiver, the photodiode, outputs a 0 when a 1 was sent. Okay? But you've got to multiply by what was the original probability that they sent a 1 anyway. Plus the probability that you output the other thing, a 1 when a 0 was sent. So you've got to multiply that by what's the probability that they sent a 0 in the beginning. So now, our symbolism for that is P of 0 when a 1 was sent by P of 1 plus P of 1 when a 0 was sent by P of 0. Now, in a typical system of Manchester encoding, whatever encoding you're using, typically you would arrange for the probability of the 1s and 0s to be equal. That makes life easier for all your filters and electrical filters and all of that in the system. You complete the full system. So these two things, P of 0 and P of 1, are each a half in the real system. So we get a half P 0 stroke 1 plus P 1 stroke 0. Now we just can finish out by substituting for these. Because or fundamental optical physics tells us that at the photo generation process, a photon in, electron hole pair out, is a Poisson statistic process. It's a Poisson distribution. There's the expression for Poisson distribution. Here. E to the power of minus the number of L. L is light, like photons, by light photons to the power of J. J is current. Right? J is the number of carrier pairs, divided by factorial carrier pairs J. So we've got to substitute that in up here. Right? Now when you do that, this one goes straight away because L is not. Okay, when a naught was sent, means there's no photons. Right? So if L is not in the Poisson thing, there's an L there, so the whole thing's not. So half the expression is gone straight away. You only have to worry about the other half, e to the minus L, and now e to the minus L photons, L photons where you generate no, error is caused because you generate no J, over factorial J, which is factorial naught. There's no output. Factorial naught is 1, L to the naught is 1, so all we're left is e to the minus L. Half e to the minus L is the probability of error. Final tidy up. Take the half up into the exponent, e to the power of 0.69 gives you the half. So that is our probability of error. The International Telecoms Union says that has to be better than 10 to the minus 9. So compare them. To compare, 10 to the minus 9, it has to be converted to power e instead of power 10. So you multiply the power by 2.3. We get 20.7. Up here, we have L plus not quite 0.7. Compare them tells us L has to be better than 20. In fact, it has to be better than 20.01 to compare the two numbers. They're bizarrely close. But you can't have 0.1 of a photon, so you need 21 photons per bit. And then you can multiply up by the bit rate and you'll get the power required at the receiver. If you go below that power, you will not satisfy the bit error rate under any circumstances. In practice, it might have to be 10 or 20 decibels better than that because there's other faults in the receiver. There's jitter, timing jitter, and there's amplitude jitter in any communication network. So in practice, you might multiply up by another 100. So that is our limit of detection. Okay, well, I hope that helps to cover the 3 sections of the course, of this half of the course. And I again urge you to redraw all diagrams, and I guarantee you it'll make life an awful lot easier. Even if you're looking at the 3 tutorials, draw the diagrams as well while you're looking at them. Thanks very much for coming along, and thanks Laura for doing the work.